Hello everyone. In this video I'll provide an overview of Section 3, Independent Events. You can see this will be a short video. We just have 3 items. We'll start with the definition of independent events. We'll take a look at some properties of independent events and then a couple of examples. The definition of independent events goes like this. We say that events A and B are independent if and only if the probability of A intersect B is equal to the probability of A times the probability of B. And of course, if we have this equation with not equals, then A and B are dependent. So some common examples of independent events would be coin flipping. In particular, if you flip a coin twice, the outcome on the second flip is independent of the outcome on the first flip. Similarly, tossing dice, if you toss a pair of dice twice, the outcome on the second toss is independent of the outcome on the first flip. And there are many other independent events out there. Some of these are sort of more theoretical, like these here, and then there's some practical situations too where people look for independent events, such as in investing in stocks. Here's a fairly simple example. Well, let's imagine a bag of marbles, let's say on the left, and we want to think in terms of what's the probability of pulling a black marble 2 times in a row. So in the first case, suppose we pull the first marble and then you put it back. Okay? In this case, the probability of pulling a black would be 2 over 10, say these two, and then we put it back, and so the probability of pulling a black on the second time is also 2 over 10. And so in this case, you can see we get a final probability of 1 over 25. Okay? Notice when you put these back, put the marble back, you get the product of the 2 probabilities. But if now you keep the first marble, then on the second try, the event is dependent because the probability of a black the first time would be 2 over 10, but having selected a black the first time, we only have 1 black left out of 9 marbles, so the probability now of 2 blacks would be, you could say, 1 over 45. A few other important probabilities of independent events is that if A and B are both positive, in the sense they both have positive probabilities, then they cannot both be independent and disjoint. Okay. For example, independent events might look something like what you see here. These 2 events would overlap, and we'd be interested in looking at the probability of A intersect B. Disjoint events, however, would look something like this. Their intersection would be 0. So again, so you cannot have both independent and disjoint events. If A is a subset of B, and neither the probability of A is 0, nor the probability of B is 1, then A and B are dependent. Okay? So when A is a subset of B, we know automatically that A and B are dependent. This is something we can prove, but for now, we'll take it as it's stated. If neither the probability of A is 0, nor the probability of A is equal to 1, then A and A complement are considered to be dependent. And if A and B are independent events, then A complement and B are also independent events. So here we have basically in this section an introduction to independent events. This is sort of going to be a recurring theme throughout the course, and we'll find other ways of determining if events are independent. So let's look at one more example in this video. Suppose we have two fair dice are tossed. Let A be the event that the sum of the two dice is 6, and let B be the event that the first die is a 4. The question is, are A and B independent events? So we go back to the definition. We must determine if the probability of A intersect B is equal to the product probability of A times the probability of B. And we could go ahead and try to calculate each side of this equation and then compare. Okay, A intersect B would be the outcome where the sum is 6 and the first die is 4. So the only way this could happen would be with the pair 4, 2. And there are 36 different outcomes when you look at tossing two dice. So the probability of A intersect B is 1 over 36. Now, A is the event that the sum is 6, and there are 5 different pairs that sum to 6, right? We would have 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. So the probability of A is equal to 5 over 36. Recall B is the event that the first die is a 4, so the probability of B is 1/6. When we look at the product, P of A times P of B, notice we'll get 5 in the numerator over 216 in the denominator, and that is not equal to 1 over 36. Right, you could see if this was expressed with 216 in the denominator, this would be 6 over 216. So we may conclude that the events are not independent. So this concludes the video. I hope you enjoyed it.